Chapter 5. Latest IT Trends. Augmented Reality. Augmented reality, AR, is a cutting-edge technology. It has gained popularity in recent years. It lays over computer-generated elements onto the user's view of the real world, typically using smartphones, tablets, AR glasses, or other wearable devices. AR enhances the real-world environment by adding digital information or objects seamlessly. AR technology achieves this by using cameras, sensors, and sophisticated algorithms to recognize and track objects and locations in the physical world, allowing for the precise placement of digital content. It redefines how we interact with the world. Key components of AR. Hardware. AR devices come in various forms, from smartphones and tablets to dedicated AR glasses like Microsoft HoloLens or Google Glass. These devices are equipped with cameras, sensors, displays, and processing power necessary for AR experiences. Software. AR applications rely on some software that integrates real-world data with digital content. It also includes computer vision algorithms for object recognition and tracking. Applications of augmented reality. AR has various applications across various industries. Some of them are discussed here. Entertainment. AR is transforming the gaming industry, which overlays virtual creatures on the real world. It also enhances live events and theme park experiences with interactive elements. Education. AR is used in educational settings to make learning more engaging and interactive. Students can explore 3D models, historical recreations, and immersive simulations. Healthcare. Surgeons use AR to enhance precision during surgery by overlaying critical patient information. It's also used for medical training and patient education. Industrial and manufacturing. AR is used for maintenance and repair tasks, providing workers with step-by-step instructions and real-time data. Navigation. AR navigation apps like Google Maps Live View overlay directions onto the real world, making it easier to find your way in unfamiliar places. Marketing and advertising. Brands use AR to create interactive and immersive marketing campaigns, allowing consumers to engage with products before purchasing. Benefits of AR. Enhanced user experience. Training and simulation. Healthcare advancements. Enterprise and industry. Education transformation. Virtual reality. Virtual reality refers to a computer-generated simulation of an interactive 3D environment that users can engage with through specialized hardware and software. Unlike the real world or augmented reality, AR, which overlays digital content onto the physical world, VR replaces the user's physical surroundings entirely with a computer-generated environment. VR aims to create a convincing sense of presence, where users feel like they are physically present in the virtual world, even though they are aware that it is a digital simulation. Key components of VR. Hardware. VR hardware includes headsets or HMDs, head-mounted displays like the Oculus Rift, HTC Vive, or PlayStation VR. These devices typically consist of high-resolution displays, sensors, and headphones to provide an immersive experience. Software. VR software includes computer-generated environment, applications, and experiences. It encompasses 3D modeling, rendering engines, and interactive elements that enable users to navigate and interact with the virtual world. Input devices. To interact with the virtual environment, users often use hand controllers or gloves equipped with sensors. Some advanced VR systems incorporate full-body tracking and feedback devices to enhance immersion. Applications of virtual reality. VR has various applications across various industries. Some of them are discussed here. Gaming. VR gaming offers unparalleled immersion, enabling players to step into the game world and interact with it. Education and training. VR is used for educational simulations, enabling students to explore historical sites and undergo realistic training in fields like aviation, medicine, and military. Healthcare. VR has applications in therapy, pain management, and rehabilitation. It is used to treat phobias, post-traumatic stress disorder, and chronic pain. Surgeons also use VR for preoperative planning and training. Architecture and design. Architects and designers use VR to create immersive walkthroughs of buildings, interior designs, and urban planning projects, allowing clients to visualize concepts better. Entertainment and media. VR is transforming the entertainment industry, offering immersive experiences in movies, concerts, and virtual theme parks. Tourism and travel. VR enables virtual tourism, allowing users to explore distant destinations or historical sites from the comfort of their homes. Social interaction. Social VR platforms like Oculus venues provide opportunities for people to meet, socialize, and collaborate in virtual spaces. Future of virtual reality. Virtual reality has the potential to revolutionize several aspects of our lives. Telecommuting and remote collaboration. VR can make remote work and collaboration more immersive and effective, reducing the need for physical presence. Therapy and rehabilitation. VR will continue to play a significant role in healthcare, aiding in physical and psychological therapies. Education and training. VR will transform education, making learning more engaging and accessible to a global audience. Entertainment and media. VR will offer new forms of storytelling and entertainment, creating unique and immersive experiences. E-commerce and retail. VR can enhance the online shopping experience by allowing customers to try products virtually before purchasing. Architecture and urban planning. VR will streamline the design and planning processes in architecture and urban development. Extended reality. Extended reality, XR, represents a spectrum of technologies that encompass virtual reality, VR, augmented reality, AR, and mixed reality, MR. XR extends the boundaries of human perception by seamlessly merging the physical and digital worlds. It offers a spectrum of experiences that range from fully immersive to subtly augmented. The XR spectrum. Virtual reality, VR. VR immerses users in entirely digital environments, blocking out the physical world. Users wear headsets to engage with a simulated reality, making it ideal for gaming, simulations, and immersive storytelling. Augmented reality, AR. AR overlays digital content onto the real world, enhancing the user's perception of their surroundings. It is commonly used in smartphone apps, smart glasses, and heads-up displays, offering practical applications in fields like navigation, education, and remote assistance. Mixed reality. MR is the convergence of the physical and virtual worlds. It allows virtual objects to interact with the real environment and vice versa. Users can see and manipulate both real and digital elements simultaneously, opening doors to innovative applications in various domains. Applications of XR. Extended reality is transforming numerous industries and aspects of daily life, fostering innovation and creating new opportunities. Here are some applications are given. Gaming and entertainment. VR gaming has gained immense popularity, providing players with immersive and interactive experiences. AR enhances entertainment by adding digital layers to live events and broadcasts. Healthcare. XR aids in medical training, surgery planning, and telemedicine. Surgeons can use MR to overlay patient data during procedures, and VR can be applied for pain management and therapy. Education. XR brings learning to life by enabling interactive 3D models, virtual field trips, and historical reconstructions. Students can explore concepts in a more engaging way. Architecture and design. Architects and designers can use XR to visualize and work on projects more efficiently. Clients can take virtual tours of properties before construction begins. Manufacturing and training. XR enhances industrial training and assembly processes. Workers can receive real-time instructions and support, reducing errors and increasing productivity. Retail. AR enables customers to try products virtually, such as trying on clothes or placing furniture in their homes before purchasing. This improves the shopping experience and reduces returns. Future possibilities of XR. The future of extended reality holds tremendous promise, driven by ongoing technological advancements and evolving user expectations. Hardware evolution. XR devices will become more compact, powerful, and affordable. This will broaden accessibility and encourage widespread adoption. 5G connectivity. The rollout of 5G networks has significantly enhanced XR experiences. It provides low latency, high bandwidth connections, seamless streaming of complex XR content, and real-time collaboration. Artificial intelligence integration. AI play a pivotal role in XR, enabling improved object recognition, natural language processing, and personalized content creation. AI-driven XR applications will become smarter and more intuitive. Enterprise adoption. Businesses will increasingly leverage XR for remote collaboration, training, design, and marketing. XR solutions will drive productivity gains and cost savings across industries. 3D printing. 3D printing, also known as additive manufacturing. It is a revolutionary technology that has fundamentally transformed the way we create physical objects. Unlike traditional manufacturing methods that involve subtracting material from a solid block, example, machining, 3D printing builds objects layer by layer from digital designs. Principles of 3D printing. 3D printing is a process that involves creating a three-dimensional object by adding material layer by layer. The key principles of 3D printing are as follows. Digital design. The process begins with a digital 3D model of the object, typically created using computer-aided design (CAD) software. This digital file serves as the blueprint for the 3D printer. Layer printing. The 3D printer interprets the digital design and divides it into thin horizontal cross-sections or layers. The printer then deposits material layer by layer to recreate the object. Material deposition. Various materials can be used in 3D printing, including plastics, metals, ceramics, and even biological materials. The choice of material depends on the specific application. Printing process. The printing process can vary based on the 3D printing technology being used. Common 3D printing methods include fused deposition modeling, FDM, selective laser sintering, SLS, and more. Applications of 3D printing. 3D printing has a wide range of applications into the different industries. Some of them are given here. Prototyping. 3D printing is widely used in product development for rapid prototyping. It allows engineers and designers to quickly create physical prototypes to test and refine their designs. Customization. 3D printing enables the production of customized and personalized products, including medical implants, dental aligners, and consumer goods like customized phone cases. Aerospace. The aerospace industry uses 3D printing to manufacture lightweight components with complex geometries, reducing the weight of aircraft and spacecraft. Healthcare. In healthcare, 3D printing is used for creating patient-specific implants, prosthetics, dental restorations, and even tissues and organs through bioprinting. Automotive. Automotive companies utilize 3D printing for rapid prototyping, producing custom parts, and even manufacturing end-use components like interior trim pieces. Architecture and construction. Large-scale 3D printers can create building components, reducing construction time and waste. Fashion and jewelry. Designers and jewelers use 3D printing to create intricate and unique pieces. Impacts of 3D printing. 3D printing has significant impacts on various aspects of society and the economy. Customization and personalization. 3D printing allows for highly customized and personalized products, catering to individual preferences and needs. Reduced waste. Traditional manufacturing often generates significant material waste, whereas 3D printing is more resource efficient. It only uses the material needed for the object being printed. Supply chain disruption. 3D printing has the potential to disrupt traditional supply chains by enabling localized and on-demand production. Medical advancements. 3D printing has revolutionized healthcare with patient-specific implants, prosthetics, and the potential to create functional tissues and organs. Innovation. The technology encourages innovation and rapid iteration in product development, making it easier for startups and inventors to bring their ideas to life. Education. 3D printing is becoming increasingly integrated into education, providing students with hands-on experience in design and manufacturing. Future of 3D printing. Bioprinting. Advances in bioprinting may enable the creation of functional human organs, revolutionizing organ transplantation and medical treatments. Space exploration. 3D printing could play a critical role in future space missions by enabling on-site manufacturing of essential components and tools. Sustainability. 3D printing can contribute to sustainable manufacturing by reducing material waste and energy consumption. Artificial intelligence integration. AI may enhance 3D printing by optimizing designs and processes for greater efficiency and performance. Consumer adoption. As 3D printers become more accessible and user-friendly, they may find a place in more households, allowing for personalized, on-demand production of everyday items. Robotic Process Automation (RPA). Robotic Process Automation (RPA) is a powerful tool that is revolutionizing how businesses operate by automating repetitive tasks and workflows. RPA robots mimic human actions by interacting with digital systems and applications, making them a valuable tool for streamlining workflows, reducing errors, and increasing operational efficiency. Key components of RPA. Robots. RPA robots are machines with software programs capable of mimicking human interactions with computer systems, such as data entry, form filling, and data extraction. Orchestration and control. RPA systems include orchestration tools that manage and schedule robot tasks, ensuring proper execution and monitoring. User interface. UI. RPA robots can interact with the UI of various applications, just like a human user, enabling them to navigate through software systems seamlessly. Process designer. RPA platforms typically offer visual process design interfaces, allowing users to create automation workflows without extensive coding knowledge. Applications of RPA. RPA has found applications across various industries. Some of them are discussed here. Finance and accounting. RPA streamlines invoicing, payroll processing, and reconciliations, reducing errors and improving compliance. Customer service. RPA bots handle routine customer inquiries, process requests, and assist in resolving issues, leading to faster response times and improved customer satisfaction. Human resources. RPA automates HR processes such as onboarding, benefits administration, and employee data management, ensuring accuracy and compliance. Healthcare. RPA helps healthcare providers manage patient records, claims processing, and billing, reducing administrative burdens, and improving patient care. Supply chain and logistics. RPA optimizes inventory management, order processing, and shipment tracking, leading to more efficient operations. Manufacturing. RPA robots can control and monitor machinery, perform quality checks, and manage inventory in manufacturing settings. Future of robotic process automation. Cognitive automation. RPA is evolving to incorporate AI and machine learning capabilities, enabling bots to handle unstructured data, make decisions, and learn from experience. Hyperautomation. Organizations are increasingly adopting a holistic approach to automation, combining RPA with other technologies like process mining, AI, and analytics to create end-to-end automation solutions. Integration with IoT. RPA can be integrated with the Internet of Things, IoT, to automate actions based on real-time sensor data, enabling responsive and autonomous systems. RPA as a service. Cloud-based RPA services are becoming more prevalent, allowing organizations to scale automation initiatives without the need for on-premises infrastructure. Enhanced analytics. RPA platforms will offer advanced analytics and reporting capabilities to provide insights into process performance and identify opportunities for further optimization. Ethical and regulatory considerations. As RPA becomes more integrated into business processes, ethical considerations related to job displacement, data privacy, and compliance will require attention and regulation. Blockchain. Blockchain is a decentralized and distributed digital technology. It records transactions across multiple computers in a way that ensures the integrity, security, and immutability of data. Unlike traditional centralized systems, where a single entity has control, blockchain operates on a network of nodes, making it resistant to manipulation and fraud. Key concepts of blockchain. Decentralization. Blockchain operates on a network of computers, nodes, with no central authority. This ensures that no single entity has control over the system. Cryptography. Transactions on a blockchain are secured using cryptographic techniques, making it extremely difficult for unauthorized parties to alter data. Immutable ledger. Once a transaction is recorded on the blockchain, it cannot be altered or deleted. This immutability enhances the trustworthiness of the data. Consensus mechanisms. Blockchain networks use consensus algorithms like proof of work, POW, and proof of stake, POS, to validate and agree upon transactions, ensuring consensus among participants. Applications of blockchain. Finance. Cryptocurrencies are the most well-known application of blockchain in finance, but it also improves cross-border payments, trade finance, and reduces fraud. Supply chain. Blockchain enables end-to-end visibility and traceability of products in the supply chain, reducing counterfeiting and improving transparency. Healthcare. Patient records can be securely stored and shared on a blockchain, ensuring data integrity and privacy while enabling efficient data exchange. Smart contracts. Self-executing smart contracts on blockchain automate and enforce contract terms, reducing the need for intermediaries in legal and financial agreements. Voting systems, blockchain can enhance the security and transparency of voting systems, reducing the risk of election fraud. Real estate, property transactions can be recorded on a blockchain, simplifying the process and reducing fraud in real estate deals. Future of blockchain. The future of blockchain holds several promising developments. Some of them are given here. Scalability solutions. Efforts to improve the scalability of blockchain networks will enable them to handle a greater volume of transactions, making them more practical for mainstream adoption. Interoperability. Blockchain platforms are working towards greater interoperability, allowing different networks to communicate and share data seamlessly. Tokenization of assets. Assets like real estate, art, and even intellectual property are likely to be represented as digital tokens on blockchain, making them more liquid and accessible. Central bank digital currencies, CBDCs. Central banks around the world are exploring the issuance of digital currencies on blockchain to enhance the efficiency of monetary systems. Privacy enhancements. Solutions like zero-knowledge proofs are being developed to enhance the privacy of blockchain transactions while maintaining transparency. Environmental considerations. As blockchain networks become more energy efficient, concerns about their environmental impact are being addressed, potentially reducing their carbon footprint. Internet of Things, IoT. The Internet of Things, IoT, is a revolutionary technology paradigm that connects everyday physical objects and devices to the Internet, enabling them to collect and exchange data. These smart objects are embedded with sensors, software, and connectivity, allowing them to communicate with each other and with human beings, leading to increased automation, efficiency, and convenience. Key concepts of IoT. Connectivity. IoT devices are connected to the Internet or other networks, enabling remote monitoring, control, and data exchange. Sensors and data. IoT devices have sensors that gather data from the environment or the device itself, providing valuable insights for decision-making. Data processing. Collected data is processed locally or in the cloud, often using artificial intelligence, AI, and machine learning, ML, algorithms to derive meaningful information. Automation. IoT enables automation of various processes, reducing human intervention and improving efficiency. Applications of IoT. IoT has a profound impact across various industries, transforming how businesses operate and enhancing people's daily lives. Smart home. IoT devices like thermostats, security cameras, and voice assistants make homes more convenient, secure, and energy efficient. Healthcare. Wearable IoT devices and remote monitoring improve patient care and enable early disease detection. Manufacturing. IoT sensors on machines and equipment enhance predictive maintenance, reducing downtime and optimizing production. Agriculture. IoT-based precision farming optimizes crop management, irrigation, and livestock monitoring for increased yields and sustainability. Smart cities, IoT solutions for transportation, waste management, and infrastructure improve urban living through increased efficiency and reduced environmental impact. Logistics and supply chain, IoT sensors track shipments, monitor inventory, and optimize routes, improving the efficiency and transparency of supply chains. Future of IoT. The future of IoT holds several exciting developments and trends. Some of them are discussed here. 5G connectivity. The rollout of 5G networks will significantly enhance IoT capabilities, enabling faster data transmission and lower latency. Edge computing. IoT devices are increasingly equipped with edge computing capabilities, enabling data processing at the device level, reducing latency, and enhancing privacy. AI integration. AI and ML play a crucial role in IoT, enabling devices to make more informed decisions, improve automation, and provide advanced analytics. IoT security. As the number of IoT devices grows, security will become a paramount concern. Stronger authentication, encryption, and device management will be critical. Interoperability. Standards and protocols that enable different IoT devices to communicate seamlessly will gain importance as ecosystems expand. Environmental sustainability. IoT will contribute to sustainability efforts by enabling more efficient resource management, reducing waste, and minimizing energy consumption. Cloud computing. Cloud computing is a revolutionary technology that has transformed the way individuals and businesses access, store, process, and manage data and applications. Instead of relying on local servers or personal devices, cloud computing utilizes remote servers hosted on the Internet to provide a wide range of computing services, from data storage to powerful computing resources, accessible from anywhere with an Internet connection. Key characteristics of cloud computing. On-demand self-service. Users can provision and manage resources as needed, without requiring human intervention from the service provider. Broad network access. Cloud services are accessible over the Internet, making them available from a variety of devices and locations. Resource pooling. Cloud providers pool and allocate resources dynamically, optimizing efficiency and scalability. Rapid elasticity. Cloud resources can be quickly scaled up or down to accommodate changing demands, ensuring cost-effectiveness. Cloud service models. Cloud computing offers various service models, catering to different business needs. Infrastructure as a service, IaaS provides virtualized computing resources over the Internet, such as virtual machines, storage, and networking. Users have control over the operating system and applications. Platform as a service, PaaS offers a platform with development tools and services for building, testing, and deploying applications. Users can focus on coding and application logic, while the cloud provider manages the infrastructure. Software as a service, SaaS, delivers software applications over the Internet on a subscription basis. Users access applications through a web browser, eliminating the need for local installations and maintenance. Cloud deployment models. Cloud computing can be deployed in different ways depending on the organization's requirements. Public cloud services are provided by a third-party cloud provider and are accessible over the public internet. Public clouds offer scalability and cost-effectiveness but may have security and privacy considerations. Private cloud, operated exclusively for a single organization, a private cloud offers greater control, security, and customization. It can be hosted on premises or by a third-party provider. Hybrid cloud combines public and private cloud resources, offering flexibility and the ability to move workloads between environments. It caters to organizations with varying needs for scalability and security. Future of cloud computing. The future of cloud computing is marked by several trends and innovations. Edge computing, processing data closer to the source or edge of the network to reduce latency and enable real-time decision-making. Serverless computing, a model where cloud providers manage infrastructure, automatically scaling resources based on demand, allowing developers to focus solely on code. Quantum computing, the integration of quantum computing into cloud services, enabling breakthroughs in cryptography, simulations, and data analysis. AI and machine learning. Cloud platforms will increasingly integrate AI and machine learning tools, making these technologies more accessible to a wider range of applications. Security and compliance. Continued focus on enhancing security measures and regulatory compliance to address growing concerns about data protection and privacy. Edge computing. Edge computing is a distributed computing paradigm that brings data processing and computation closer to the data source or edge of the network, rather than relying solely on centralized cloud servers. This approach aims to reduce latency, enhance real-time decision-making, and improve the efficiency of data transmission by processing data locally or in nearby edge servers. Key concepts of edge computing. Low latency. Edge computing reduces the time it takes for data to travel between devices and data centers, enabling quicker responses and real-time applications. Decentralization. Unlike cloud computing, which centralizes data processing, edge computing disperses computing resources across various edge devices, gateways, and servers. Data filtering. Edge devices can filter and preprocess data locally, sending only relevant information to the cloud or data center, reducing bandwidth usage. Reliability. Edge computing can enhance the reliability of applications by reducing dependence on a single centralized data center or cloud provider. Applications of edge computing. Edge computing has many applications across various industries, enabling new possibilities and improving existing processes. IoT and smart devices. Edge computing enhances the capabilities of IoT devices by enabling real-time data processing and local decision-making. Autonomous vehicles. Self-driving cars rely on edge computing to process sensor data quickly, ensuring safe and efficient navigation. Healthcare, medical devices, and wearables benefit from edge computing for real-time monitoring and timely alerts to healthcare providers. Manufacturing, edge computing in manufacturing improves automation, predictive maintenance, and quality control by processing data at the source. Retail, in-store edge devices can personalize shopping experiences, optimize inventory management, and enhance security. Telecommunications, edge computing enables content delivery networks, CDNs, to reduce latency for streaming and online gaming. Future of edge computing. The future of edge computing holds several exciting developments. Some of them are given here. 5G integration. The rollout of 5G networks further supports edge computing by providing low latency, high bandwidth connectivity. Fog computing, an extension of edge computing. Fog computing distributes computing resources even closer to the data source, often at the network's edge. AI and machine learning. Edge devices will increasingly incorporate AI and machine learning algorithms for real-time data analysis and decision-making. Security and privacy. Enhanced security measures will be critical as edge devices become more prevalent, ensuring data protection and privacy at the edge. Edge-to-cloud orchestration, efficient coordination between edge devices and cloud resources will be crucial to leverage the strengths of both paradigms. Energy efficiency. Innovations in low-power computing and renewable energy sources will make edge devices more energy efficient and sustainable. In summary, augmented reality, AR, is a cutting-edge technology. Virtual reality refers to a computer-generated simulation of an interactive 3D environment. Extended reality, XR, represents a spectrum of technologies that encompass virtual reality, VR, augmented reality, AR, and mixed reality, MR. 3D printing is a revolutionary technology that has fundamentally transformed the way we create physical objects. RPA is a powerful tool that is revolutionizing how businesses operate by automating repetitive tasks and workflows. Blockchain is a decentralized and distributed digital technology. The Internet of Things, IoT, is a revolutionary technology paradigm that connects everyday physical objects and devices to the Internet. Cloud computing is a revolutionary technology that has transformed the way individuals and businesses access, store, process, and manage data and applications. Edge computing is a distributed computing paradigm that brings data processing and computation closer to the data source.